So we'll look at more designs. So in this slide that I was using that index 3 in the beginning to say that we are averaging the first 3 eigenspaces, right? So don't pay too much attention to it. Let's just, don't worry about the number 3, okay? So this is the icosahedral graph. We saw this yesterday. We saw some designs on it, right? So let's actually systematically compute those designs. So here are all the eigenvectors of the icosahedral graph. Okay, this is for the walk matrix. This is for 1 over dA, okay? And the bands, the strips are just the different eigenspaces. So there are 4 eigenspaces. The first one is trivial, and then there are 2 3-dimensional ones and 1 5-dimensional one eigenspace. Okay, so I want to average eigenspace 3 and eigenspace 4. That's the blue stuff. Okay, I want to average the blue, so everything that's not pink. So eigenspace 3 and eigenspace 4, which is blue, I want to average. So the polytope is going to come from the pink part. Do you agree? I have to take the complementary eigenvectors, which is pink, and I'm going to convexify those columns. So remember here the phi means the golden ratio. It's 1 plus root 5 over 2. Okay, it's a number. Okay, it doesn't matter what it is. It's a number. So what do you think this will be when you convexify? Here in this example, I think we also have 12 vertices, right? 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. Okay, so there are 12 things. And the important piece is this part. This is just all ones. That's not important. So we expect a 3-dimensional polytope with maybe 12 vertices, right? Is there any doubling, like in the previous example?
Yes.
There is doubling?
Well, consider a vector and its negative to be the same?
No.
Okay.
Vector and negative is not the same. Because that is really 2 things. I need them both when I take convex hull. Yeah.
So every vector seems to have its negative.
Yeah, so it's probably symmetric. This polytope is probably symmetric. But this really seems to be a 3-dimensional polytope with 12 vertices.
Yeah.
Does everybody agree? There's no obvious doubling of columns happening here, okay? And this is kind of a miraculous example because if you convexify these 12 columns, you get the icosahedron back. Okay, we started with the icosahedral graph, but the convexification of the pink part is an icosahedron. Okay, this is like, there's a reason for this. So Gottzel and all studied this for a while. So they were interested in graphs for which some eigenspace, when you compute the eigenpolytope, gives you a polytope whose graph is the original graph. Okay, so there's some, so I think like distance transitive or something like that has this property. They were interested in this. This is one of the reasons he defined eigenpolytopes. They're interested in embeddings of graphs, right? So if I have a graph, maybe it is the graph of a polytope. That would be a nice embedding. So in this is an example of such a thing. Okay, it's an icosahedral graph, but you can forget that it came from the icosahedron. But then when we convexify this one eigenspace, you get back the icosahedron.
Okay. Distance transitive graph always satisfies this result?
Something like that. I forget exactly what their result is. So I think at least some distance transitive do. They characterize the graphs that satisfies this property. Okay, so it's again an icosahedron. So this is the icosahedron. So that means all its facets are triangles, right, in the icosahedron. So then, do you see what the designs will be, the minimal designs? So facet will have 3 points. So every minimal design should be the complement, right? I need the complementary vertices to find my design, and those are exactly, so they'll always have 9 points. Every minimal design will have 9 vertices, right? It's the complement to what's on the facet. And here everything is drawn on top of each other, right? So this picture here is both the graph and the eigenpolytope and everything. So you see the design is sitting on these pink and red vertices. They don't all have the same weight. That's why some are pink and some are red. But every single minimal design will have size 9 in this example. It was the same in the previous example, right? Every design had the same size. Is this clear? What's happening? Please ask a question if this is not clear. Okay, so the claim is that the design that has the pink and red weights, that if I take the weighted average of any of these white eigenvectors with those pink and red weights, I will get the global average. That's what this is saying.
So
Okay.
by symmetry for lambda 3 also you should get it.
Yeah, so for lambda 3 by symmetry, probably you have the same thing. Okay? So the more interesting one is lambda 4. So let's try to see what happens there. So, all right. So this is the next piece. So now I want to average lambda, the second eigenspace and the third eigenspace. That means I need to convexify everything pink. Okay? So now we cannot, okay, it looks how many, what's a dimension? 1, 2, 3, 4, 5, right? If you look at the bottom eigenspace, it has 5 rows. The all ones doesn't add to the dimension of the polytope.
But there is doubling.
But there's doubling. So do you see what's happening? What is that polytope actually? I actually wrote the answer there, but take a look. So
6 vertices.
6 vertices in 5 dimensions, right? So just check that every column pink is doubled, right?
First and second, third and fourth, fifth and eighth,
Yeah,
sixth and seventh.
yeah. Okay, everybody okay? Every column appears twice. So there are really only 6 vertices, and the polytope is 5-dimensional. So what could it be?
No, it could be sitting in a lower dimension.
No, it's not. It's really because of the eigenvectors being independent, right? This really is a 5-dimensional polytope when I convexify the columns.
Because you said the rank is...
The rank of the pink part in the bottom is 5. So there's no rank drop. This is very nice about these examples, okay? So I know I'm going to get a 5-dimensional polytope. It happens to have 6 vertices because of the doubling. So what can we do? The only polytope in 5 dimensions with 6 vertices is the simplex, right? Think about it. In 2 dimensions, the only polytope with 3 vertices is a triangle. That's a simplex. In 3 dimensions, you need at least 4 vertices to make a 3-dimensional polytope, and that's the tetrahedron. That's a simplex. So in any dimension, if you only have one more vertex, like d dimensions, d plus 1 vertices, it has to be a simplex or something lower, as Arvind said, but lower dimensional, but that won't happen because of the fact that the rank of the pink part is 5. Okay, so this is a simplex. So it's a simplex, and every vertex carries 2 labels, right? Because there's a doubling. So every vertex of this simplex, which has 6 corners, will carry 2 labels, right? So what's the size of a facet of a simplex? Can we just work that out? So this is all in high dimensions. I'm not going to be able to draw a picture, but if I take a facet of delta 5, this is the simplex that this polytope is, right? So the simplex has 6 vertices. So how many vertices on a facet? Like think tetrahedron. Tetrahedron has, 4 vertices in 3 dimensions. On a facet we will have 3 and 1 will be left out, right? In a simplex always one guy is left out. Facet, one guy is left out, right? Triangle, so tetrahedron is maybe better. So tetrahedron, that's a tetrahedron. So if I take a facet, one thing is left out. If I take another facet, one thing is left out, okay? Okay, so let's decide the size. So here I have a facet of delta 5 has how many now? 5 vertices. But in this example, how many labels does that facet carry? 10, right? Because every label is doubled. at a corner. So it really carries 10 vertices. So really in our example, it carries 10 vertices, right? It carries 10 things. So the complement has size 2, okay? So these are all designs of size 2. The designs that can average the blue eigenvectors. And you see them here in the picture, you see? They're like these opposite points in some sense. And they're uniformly weighted too in this example. So we're saying that all the minimal designs have size 2, and all the minimal designs come from the different facets of the 5-dimensional simplex. Do you know how many facets there are for a simplex? Just extrapolate from triangle tetrahedron. Triangle 2-dimensional, 3 facets. Tetrahedron 3-dimensional, 4 facets. 5-dimensional simplex, 6 facets. So there should be 6 minimal designs, each of size 2. This is okay? All right. So this one looked complex, but it wasn't. It was really nice, okay? Okay, so tetrahedron, this one we just did before. This is okay? So this, I'm just averaging everything except these 2. This is on purpose so see, this is an example of an extremal design. I'm averaging everything except one eigenspace. Okay, this is an extremal design. If I wanted to take the polytope from this one or this one or this one, you have to work harder. Or if you want to take 2 at a time, that you have to work harder. Okay, so this one is purposely like this so that you have a very easy example. Now let's do a hard example. This is the Peterson graph. Okay, this is a hard example actually. So again, the eigenvalues are on top. Okay, so this graph has 10 vertices, so there are 10 eigenvalues with multiplicity. So the first one is 1 with multiplicity 1. So the little bracket thing on top of the number gives the multiplicity. Okay, so 1 appears with multiplicity 1, minus 2/3 with multiplicity 4, and 1/3 with multiplicity 5. Okay, so there are 2 fat eigenspaces of dimension 4, dimension 5, and 1 guy with the trivial one. Okay, so this U2 bar means I want to average the second eigenspace. So this is the complement. Okay, these are all the eigenvectors that I don't want to average. So it should have 5 rows from the 1/3 eigenvalue, right? And then the all ones. Okay, so these are all the ones I don't want to average. So the columns of this is what I have to convexify. Okay, and this should be a 5-dimensional polytope with maybe 10 vertices, right? Could be 10 vertices. Nothing is doubled. Maybe you can quickly check for at least one thing. Nothing is doubled, I claim. Okay, so this is really hard. This is really hard to do by hand. Okay, but we have software that can count facets and faces and so on. Maybe one of the best ones is Polymake. So Polymake is a software that runs through Julia. It also runs through inside this. It's a standalone thing too, but I think it's also inside this thing called Oscar, which is like the big conglomeration of software that came out of Berlin. But there's a package called Polymake. You can call it through Sage Math as well, if you know Sage Math. So this package will compute for you, if you give it vertices, it'll compute for you the facets, it'll count how many facets, how many edges, how many vertices, how many ridges, all kinds of things. It'll collect all faces, okay? So we ran it through that, and then you see this has 10 vertices, so none of the vertices double up. It'll really have 10 vertices, it'll have 45 edges. These are the 1-dimensional faces, these are the 0-dimensional faces. It has 90 2-dimensional faces, 75 3-dimensional faces, and 22 facets. Okay, so this we cannot do by hand. I don't see a way to do this by hand. But there's a group action on this, on the facets. Okay, so there's only 2 types of facets. Those 22 facets come in 2 types. This also Polymake can find for you. It can actually tell you the symmetry group of the polytope. It can tell you up to symmetry how how many things there are, right? Like in a tetrahedron, there's only one type of facet, right? There's a triangular facet, and it's repeated everywhere. So it's really only one facet up to combinatorial type, or up to group action. Group action means like the automorphism group, I guess, of the polytope. Okay, so it turns out that these 22 facets come in two types. 12 of them are simplicial. That means that 12 of them are simplices. Okay? So this is a 5-dimensional polytope. So the facet is 4-dimensional. So 12 of these facets are 4-dimensional simplices. And the others have 6 vertices. Okay? So if you have a 4-dimensional simplex, how many vertices do you have on it? 5. Okay? So 12 of them have 5 vertices on them, and then 10 of them have 6 vertices on them. There are 2 types, okay? So that means the designs, which are the complement, will have 10 minus 5 from the first type, and 10 minus 6 from the other type. So either they are size 5 or size 4, okay? And those are the 2 pictures you see there. So either you get size designs with 5 things, 5, Yeah, I think those are all uniform. And then there are these other ones that are not uniform. So here they are. Okay, so this is a smaller design, but the weights are more tricky. The other one is a slightly bigger design, but the weights are uniform. Good? So this is an example of one. I couldn't do this by hand. Like you need some software to understand what's happening, unless you know something extensively about the Peterson graph. Okay. So you need software to do almost everything in this business. There's nothing almost that you can compute by hand. Okay, so those are all the examples, I think. Oh yeah, let's discuss this. This is actually interesting. So from this theory, right? Oh, we have it. Okay, it's interesting, but let's skip it. Okay, let's come here, okay? So this whole theorem that we just learned, right? It's saying that all the designs are organized on the faces of this eigenpolytope. So you tell me which eigenvectors to average, you take the complementary set of eigenvectors, form the polytope, and all the designs are sitting on its faces. The minimal designs are sitting on the facets, the bigger designs are sitting on the smaller and smaller faces of the polytope. We usually only look at the facets, okay? But that tells you that you can walk between designs, right? So think of the dual graph. So by that I mean, how do we draw?
You have a different polytope for every different field, right?
Yeah, different polytope. So depending on what you decide to average, once you fix that, you get one polytope, which is from the complementary eigenvectors.
Okay, you're not changing the field. You're fixing this field, capital field.
In this, yes. So in this, yes. So let's fix the yellow phi, and you get a polytope from the green part, which was pink in the slides. And then it has lots of facets. Yes. Every facet carries a minimal design for that phi, right? But what I'm drawing here is, so remember previously we saw Peterson, right? It had 2 types of designs, this type and that type. They both sit on 2 facets. So this picture I'm trying to draw here is showing you, here is one type of design. It's connected to these, so this facet is adjacent to this facet. This is like the dual graph. How do I draw this? Okay, let's do it on the cube because everybody likes the cube. So what we're doing is, if suppose my eigenpolytope is the cube, so every facet of the cube carries a minimal design. Okay, so this facet carries one design, but this facet is adjacent to this facet, the back facet, and the bottom facet, right? So there is a graph that I can draw where I put a vertex in the middle of every facet, and then I connect the vertices together if the facets are touching in a one lower dimensional face, okay? So in this case, I connect these 2, I connect those 2, I connect those 2. Do you see what I'm saying? This is called the dual graph. Okay? So in the middle of every facet, put a vertex and connect two vertices together if the facets intersect in a dimension d minus 1 face.
How is another facial outside of that cube, the outside, they consider it as one of the faces. We connect also.
No, I'm not trying to do that, okay? I'm just trying to find adjacencies among facets, right? You can walk from facet to facet, but just don't walk through some low-dimensional face, okay? Don't go from this facet. So in this example, all the facets are nicely touching each other, so it's hard to draw. So this is the picture. This is like the dual graph picture, right? So on every facet, this design sits on a facet, and that facet is adjacent to all these facets, and these are the designs that sit on them. That's what this is showing, okay? And 1, 2, 3, 4. Yeah, so here I didn't have the pink picture, but you see that this 5 cardinality design is not connected to any other 5 cardinality design. All its neighbors are 4 cardinality designs. But then if you walk from here forwards, you might get another 5 cardinality design, right? So these designs are, so and this is not a complete picture. This is just one facet and its neighbors. Okay, so it's not a complete picture. So it goes on and on and on, right? This is a 5-dimensional polytope. So this is just a local picture of one facet and all the neighboring facets, right? But there is this sort of graph structure on the designs themselves that allows you to walk among designs. And it also shows you that combinatorial designs may be completely surrounded by non-combinatorial designs, right? The 5-vertex one was uniformly weighted, the others were not. Sorry, they're not pink anymore. And then bigger designs sit on the things that connect this facet to this facet, like this edge in this example. So there's a whole like structure to how they're organized. That's all I'm trying to say. Okay, and then here is an example of a big design. Okay, so this is a graph. This graph has 229 vertices. No, sorry. It has 2,277 vertices. So it's the network of all English language Wikipedia pages that are related to chameleons. Okay, so there are large databases of graphs. This is a real graph of all the Wikipedia pages that talk about chameleons. Okay, so vertices represent pages, and edges join pages that are mutually connected by hyperlinks. So if you have one page that links to a different page, you put an edge. Okay? So this is a graph, and this is a 220, so this graph really has 2,277 eigenvectors, right? Because that's the number of vertices. So the U matrix has this size, and these red dots will average 229 eigenvectors among the 2,000. So about 1/10 of the eigenvectors will average. Okay? So this is just a fun example, and this is in this article by Catherine in the notices called "What is a Graphical Design?" So,
Just one question.
yeah.
In the Wikipedia, if you search like chameleons or whatever you say, so in the explanation, we get different kind of hyperlinks.
Yeah.
Like, so that is not considered as an edge, right?
Every hyperlink is if a page links to another page, you put an edge.
That is not related to that graph.
Put,
Like it is hyperlinked with Peterson graph.
no, it's we're only connecting to pages that again talk about chameleons. Yeah, not pages that'll talk about, I don't know, something else. Yeah. So this all pages that talk about chameleons and how they are related to each other. You can download these graphs. These graphs are available in some database. I think she got this from somewhere. If you read the article, you can find out where she got this. So tons of graphs. There are loops. Yeah, in this example, there are loops. Yeah, that's, so they reference themselves. That's really weird. Okay. Who knows? Sounds very vain, right? But yeah, it's a vain graph. that is,
Maybe it looks like a self-reference, but maybe that's a next.
yeah, it's really hard to see. It's a huge graph. It does look like a loop, you're right. Yeah. It's definitely not regular. Yeah. So you can extend all this theory to non-regular graphs. And this, again, is in a paper by Catherine. But anyway, these are just some examples of designs. Okay. What are they good for? They're good for things like sampling, right? Like this example I gave you with cholesterol or blood pressure or whatever. So if you have a big function on this graph, I want to know its global average. If it's relatively smooth, I know that it is in the span of the first so many eigenfunctions. So it's enough to average those low eigenfunctions. I can average the graph, right? So then we run this program, we find designs that can average those eigenfunctions, and those are going to tell me how to put weights on the vertices of the graph so that when I take a weighted average of the function at those vertices, I will get the global average. That's sampling is a big use of, well, I don't know if it's big use, but it's a natural use of something like this, right? Yeah. So that is the story of designs. I think there's more here, but we don't have to do it. Yeah, so about hypercubes and so on, but let's not worry about it. So actually one interesting question which I put in the open problems is, so you can study, for example, what are the designs on the hypercube graph, right? It's like the nicest graph. What are the designs on the hypercube graph? So on Friday in the colloquium, I'll talk about what we know for the Laplacian. But again, one of the things that Catherine proved is that if you take the Hamming code, it's a pretty good design. It's a pretty good extremal design. And I think there's a lot of nice things you can think about, like if you take the world of codes, so codes are subsets of 0, 1 vertices, right? They're subsets of the hypercube vertices. Then there are lots of codes. There's, Hamming is probably the most well-known, but there are BCH codes. There are, I don't know, thousands of codes. So you can ask, like, are they good as designs? Are they, so what's the point of coding theory, right? They want to space out the code words so that when you send a message and there's a mistake, they can correct the mistake. So code words should be nicely spaced out, which is similar to like a design. So if you want to average a function, you can't put all your weights and all your vertices in one corner of the graph. That's not going to work out, right? So you probably think that the design is like nicely spread out so that it captures the whole graph, right? It's representing the whole graph. So codes and designs are kind of philosophically similar. So you could check, like, are BCH codes good designs? So there's like an infinite number of problems. There are fat books on coding theory. You can open them and see if this is a good design. And maybe it's a good design for L, but not for A, or the walk. So different matrices will have different types of designs because their eigenvectors are the same, but they're going to rearrange to give you different eigenspaces, right? The eigenspaces are different. So whether you use L or walk matrix or A, you're going to get different answers. Then there's even more stuff. There's something called normalized Laplacians. There's many matrices you can attach to a graph. Okay. All right. So having said that, can you prove that no proper subset will average every eigenvector? Let's prove it. No proper subset of vertices can average all eigenvectors. That means I cannot take a W or a A or whatever we're calling it, A, that has smaller than full support. So I cannot have something smaller than full support that will average every single eigenvector. Okay?
Every single or that much what you consider? No.
Every single. So I'm claiming that there's no design, there's no subset of vertices, proper subset of vertices with weights. That means choice of A vector, where some things can be 0, that can average phi1, phi2, phi3 all the way to phi n. Just try it. It's going to come out really fast. You have an answer already? Phi2, yeah. So let's try phi2 to phi n and see what happens. Let's try, yeah, that's a good point. So let's pick an A such that phi2 transpose A is 0, phi3 transpose A is 0. and then see what will happen to such an A. Yeah, so we're supposing that there is an A such that phi2 transpose A is 0 all the way up to phi n transpose A is 0. And the support, and the support of A has size less than n. So suppose this happens. So what should A be if it can do this? Exactly. If A can do this, that means it's orthogonal to phi2, phi3 all the way to phi n, right? What's the thing that can be orthogonal to all of them? Has to be a multiple of 1, right? So if this happens, then this implies that A must be a multiple of the all ones. Okay? But this implies what? What's the size of its support? Yeah, this implies that the support is n. Okay? So this is not possible. So there can be no proper subset of vertices with weights, that's the A vector, that can average everything. So you got to leave out at least one eigenvector and one non-trivial eigenvector if you want to look for designs that are proper subsets. Everybody okay? Okay, so that was one piece. There was another one, right, like this in the exercises.
Every subset can average the...
All ones, yeah. So is that clear? We kind of discussed it a little bit in class, that every subset can average all ones. Every A can average all ones, right? Because if you have, why is that? So if you take all ones and you take any A, this will be the sum of the AIs, right? So then I can, and you know that the average of this is, the all ones is, the average of the all ones is what? N by n, 1, right? So, oh gosh. Average of 1 divided by n is 1. So this is the average. So all we need to do is to scale the A by this to make it work. So everything can average 1, so we don't need to worry about the all ones. And nothing can average everything, unless it's the whole set, okay? So those are two things to remember. Okay, so how about doing in the exercises? Yeah, so this truncated tetrahedral graph is back. So you can pick either problem 1 or problem 2 on the second page. So the truncated tetrahedral graph is back here with all its eigenvectors. And the question's asking you to compute P3 and P4. By that I mean the eigenpolytope from eigenspace 3 and 4. Maybe you can compute it and compute those designs. Is the question making sense? So this is the first question on page 2. So by P2 and by P3 and P4 I mean convexify the columns of the third eigenspace and separately also the fourth eigenspace. So those columns are 0, 1, -1 things. They're not so easy, but maybe you guys can do it. You have to draw and see what it'll look like. Or you can also use Mathematica if you have it. You have the code, right? They have the code from the morning?
Yeah.
Yeah. So in the morning we saw code to convexify things, right? We move them around and all. So you could stick it in there if you're not feeling very energetic. Or you can try to, okay, let me write it here. So let's try P3 for example. So the columns are 0, -1, 0, -1, 0, 0, 1, 1, 0, -1, -1, 0, 0, 1, 1, 1, 0, -1, -1, 0, 1, 1, 0, 0, 0, -1, -1.
Oh, this is what we said.
What?
Isn't this what we said earlier that there's doubling, everything doubling?
No, there is.
Everything is a negative.
Yeah. So in the very last eigenspace, there was doubling and it became a triangle. In this one, is there doubling? Maybe there's some doubling.
No, not doubling. Sorry. I mean, everything and its negative is there.
Is there? Okay. Yeah, that makes it a little bit easier. So these two are negatives. Everything in its negative is there?
Yeah.
Okay.
The first and the second last are negatives.
So that's kind of good. It's sort of saying that these are there and their negatives are there.
This and this. Right?
Okay. And 1, 1. Mm-hmm.
And these two.
Yeah. And yeah, these two we already did.
This we did.
And that one is,
These two.
yeah.
And this.
Okay, great. So there's a lot of negatives, but they're not doubled.
Yeah.
So you still have to kind of work. Not so easy. So either plug it into Mathematica and just look at the picture if you have it. Or just plot it and see if you can see where the facets are. It's kind of all sitting on the, they're nice points, right? They're not so bad. I'll plug it into Mathematica and see.
We have E1, E2, E3, right?
Yeah.
E1 so we have the faces of the sides of the vertices of the octahedron.
Mm-hmm.
And then 1, 1, 0.
Yeah. I already solved it.
Actually, did the same thing there.
You get it? Excellent, excellent.
I think you have already solved it.
I did it? Okay.
Shown on the slides that when you did, you get the same thing.
Oh, you already?
So they're saying that Mathematica.
Oh, I see.
But can you read off, it's a little bit, maybe you can read off facets, right? Can you? Can you roughly connect that picture to this picture? Yeah, I know, but it doesn't tell us the facets, right?
Yes, ma'am.
You kind of need to know what's connected to what. Just rotate it a bit. So it has some triangle facets and some square facets.
Here one is there, this is.
Yeah. So do you see how to place it in that way? Yeah, kind of looks similar. Okay, but at least from the picture, you can see the size of the designs, right? Minimal designs. So every facet is either a triangle or a square. So every minimal design should have size at, how many there are here? 10? 12. 12.
So 9 or 8.
9 or 8. Every minimal design has size 9 or 8. So that much we know. So just change the numbers to do P4. If I already did P3 for you, you can just change the numbers and see what happens. Did everybody get this? Do you have a question?
Oh, P4 has doubling.
P4 is doubling. Do you need help on the P3 discussion that just happened? Swami, okay? Okay.
So there are only 6 vertices.
P4 has only 6 vertices.
Oh, actually there's a tripling.
Yeah, P4 is very nice, right? There's a tripling of vertices.
So there are only 4 vertices.
in three-dimensional space.
Yeah, so it's E1, E2, E3 and minus E1, minus E2, minus E3.
Okay.
So it's like that.
So it's a simplex.
Yeah. Not a unit simplex, but
Not a unit simplex, but a three-dimensional simplex, right? Do you agree?
that makes things much nicer, right?
Yes.
Because every vertex has 3 coordinates.
Can I help you? Are you okay? This okay? Okay. All right, great. So yeah, we don't exactly know where the facets are, but you can see the size of the designs. Okay. All right, so maybe this is not so bad. Oh yeah, okay, you're drawing it. Yeah, so that's kind of you can experiment with this and find more examples. Actually, there's a whole gallery of designs. Maybe see if I can find it. Yeah, okay, I'll put the graphical designs. Okay, so it's called. You can see lots of pictures if you go to this site. You can click on each one and it tells you about the graph and the design and everything. So it's all one word, graphical designs, stuck together.
I think on one of your slides you had that.
Yeah, so this is a gallery that was made by Catherine, my student, and you can see all the designs. If you click on it, you can find out about the design. It's kind of fun.
So where did you have designs? Which mathematical file? I'm a bit confused. This one? This did not have designs. That we
No.
did today morning.
This doesn't have any designs.
Yesterday's?
Yesterday we just had the cube graph at the end
Yeah.
that we looked at and then thought
this-
about what the
yeah.
designs are.
Yeah, this
Yeah,
is
so there isn't anything much with designs because you really have to do this type of stuff. So I don't think any mathematical file has too much of designs. Yeah.
Yeah,
Okay.
you have the link here.
Okay. Oh, right. Okay. So in the Mathematica file, there's a link to the site. So that may be everything we have today, right? So if you have questions, I'm happy to answer, but if not, I think that's basically all we had for today. To find the weights W? No, you don't need L1 minimization. You can actually just, so once you know the support, you can either solve for it. Exactly, right? Or you have to use that trick that I told you where you move the, yeah. Maybe you can try to prove it even, that that's what the weights will become. But yeah, once you know what the supports are going to be, then it's easy to find them, right? Because you just restrict the weight. Sorry? Yeah, so put zeros for everywhere outside the support, and then you have a smaller system to solve, and any solution to that is okay. You cannot, okay, once you know the support, yeah, you can find it in polytime. No, no, no. In fact, these things are quite hard because, yeah, there are a lot of complexity results. So if you have a polytope and you want to know whether all its facets are made of simplices, so like in the icosahedron, every facet was a triangle, right? Those are called simplicial polytopes. That means every facet is a simplex. So to decide whether a polytope is simplicial is NP-hard. Okay? So simplicial is the best. I mean, yeah. So that means, okay, you know that every facet is at least a simplex in the sense that every facet has at least d vertices if the polytope is d-dimensional. So you know that the complement has size at most n minus d, right? So there is a natural bound on the size of a minimal design, which is this n minus d. But if you want to know whether there are designs of smaller size, that means you need to know whether there are facets with more than d vertices, right? Like in a square, like in a cube. But that is NP-hard because it's hard to know if the whole polytope is simplicial. Is there any facet that has more than simplex many vertices? That's NP-hard. So to really decide if there are facets of smaller size than n minus d is hard. Yeah. So there are a lot of complexity problems, complexity results about designs.
One solves the L1 minimization.
Yeah, if you solve L1 minimization, you get approximately correct. Yeah, which is I think how Catherine created these designs. I don't think she computed the eigenpolytope. I think she's just finding lots of designs by running L1 minimization.
Check whether how many.
So I don't think she's claiming they're minimal. She's just claiming they will average so many eigenvectors. In some cases, maybe she knows it's minimal. Meaning? Oh, no, I don't think we have any results like that. That would be interesting to know that solving L1 minimization is always going to get you the minimal designs.
Not for graphs.
Yeah, not always, but in some class of graphs, yeah, correct. No, that's just, it's only a heuristic, and we don't have any, I don't know any results like that. Yeah, that would be interesting. I know. Some of them are really huge, but you can solve linear programming with a large number of vertices, right? I mean, yeah, that's massive.
You were telling that every polytope can be an eigenfunction. There's a graph associated.
Yeah.
That graph is regular or?
I don't think it's regular or anything. It's even weighted. So I think the result is that there is a weighted graph that has some eigenpolytope that will be affinely equivalent to the polytope that you started with. I don't remember exactly how it was proven, but you can look it up. It's in one of Catherine's papers. Sorry? No, it's not very sophisticated. I mean, it's not very difficult, but it takes some cleverness. Yeah. So that's a big result, I would say, like the fact that its eigenpolytopes are universal. That's how you say it in math. It's saying that it's as bad as any polytope. There's nothing special about eigenpolytopes. Yeah, that's what it's saying.